Hey everyone, how goes it? Welcome back to CSCE552 Game Development. I'm your instructor, Dr. JJ Shepard, and today we're going to continue our discussion around game development. In the past lectures, we have focused on the concepts and the roles related to game production. We began discussing game development in a previous lecture. Today, we continue this discussion by demonstrating a few examples. We turn our attention back to the programmer and continue discussing elements related to the technical design document. We explore even more about game programming today. In a previous lecture, we discussed some values and concepts related to software engineering. Creating a video game is an exercise in software engineering. A software development process helps to plan and manage the tasks required to create software. A software pattern is a general, reusable solution to a commonly occurring problem within a given context in software design. Some common software pattern categories are structure patterns, behavior patterns, creator patterns, and concurrency patterns. We then focused on a particular behavior pattern used frequently in game software called the game loop pattern. The game loop pattern helps to organize the game's behaviors into common occurrences. Each game loop iteration progresses the game. The event step involves gathering information about occurrences that have happened since the last game loop iteration and applying necessary actions related to the event. User input, collision detection, message handling are common events. The update step modifies the data periodically based on the previous events and data. Moving the player, destroying an asteroid, collecting a coin are tasks commonly performed during the update step. Finally, the draw step displays the results of the update. As mentioned, there are steps that may appear to exist outside of the game loop pattern that we need to consider. The initialization event is when all the data or resources for a game are created and set to default values. This event only occurs one time, and it is to start the game loop. Within game code, this usually corresponds to the programming function called start, begin, or init. In contrast, the finalization event is when all the data is deallocated from memory. This occurs one time to end the game loop. In code, this usually corresponds to a programming function called end, stop, or destroy. As both of these events only occur once, they could be considered outside of the game loop, but in the end, they are just very special events. This concept can be used to create most games. However, if we were to create a more advanced game, then we need to consider some additional design and planning. More game features required more sophisticated software structural organization to better organize the behaviors shown in the game loop pattern. Speaking broadly, video game or just game software is the entire collection of the game-specific code, libraries, systems, and engines that compose a video game. The game software system is the code which runs or drives the game. Typically, it is foundational software that calls or invokes the game loop pattern functions that we write in the game-specific code. It contains software libraries used to write game-specific code. However, this is commonly considered separate from game-specific code. As mentioned, that it is foundational code that we build our specific games from. A game engine provides many of the features common in most modern games. We do not need a game engine to make a game, but as a developer, it can speed up the process. We keep in mind that game-specific code is the software specifically developed to create a game. It is separate from the game software system. Most commonly, it uses provided features and programming interfaces provided by the game system. A game engine is a software framework for developing games. It includes necessary software libraries and supporting programs. The engine contains graphics libraries, a physics engine, input manager, audio manager, message passing, and etc. Once more, a game engine is not required for making games, but it may speed up development time. Game software structure can be viewed in a slightly different way than most typical object-oriented designed software. Entity Component System, ECS, puts more stress on composition over inheritance. It focuses on not what it is, but what it does. We also keep in mind that composition was another version of association, or the has-a relationship between classes. This is related heavily to concepts in the observer pattern or mediator pattern. The component allows a single thing or behavior to span multiple domains without requiring specific relationships to each other. It is a decoupling pattern, and it has much in common with the composite pattern, where programming objects are composed of other programming objects. Component-based development emphasizes the separation of specific functionality with respect to a wide-ranging functionality available throughout a given software system. Components for a game are classes of behaviors. We create classes of behaviors instead of classes of things. This is opposed to hard-coding functions or methods within one large monolithic class, meaning writing everything in one programming file or writing all the code in a main method. The code for components are based on the game loop pattern. Separate functions for events, update, and draw are expected. Typically, within a game engine, there is a component programming interface, for which all components implement the game loop functions. Game objects are the abstract nouns in a game. Every thing in a game is a game object. Every object, player, every enemy, every rock is a game object. Game objects are considered entities in relation to the entity component design. They are simple containers for components. In many cases, game objects can be considered components themselves. Generally, classes are not specifically created for different game objects. There is no class written for player, for enemy, for exploding barrel, for heads-up display. Game engines commonly have a universal game object data type, which is not intended to be extended via programming inheritance, but instead just acts as a simple container for components and some additional metadata. Game objects are differentiated based on what behaviors they may perform. The difference is not in the data type, but rather how it behaves. By using this structure, it allows for functionality to be abstracted. Many game objects perform the same actions, so they may share the same components. We can see both player and enemy move and draw. We can consider writing one class move and another class draw and simply adding those to the player and enemy game object. The component's attributions may be different in each instance, but the component does the same action. A player's speed and an enemy's speed may be different, but they still move the same way. From a functional standpoint, they do the same actions, but with different values. Game objects may swap in and out different behaviors. The flexibility of being decoupled can allow some game objects to either gain or lose abilities. Writing game code requires understanding what are the nouns, the things, and what are the verbs, the actions or behaviors in the game. One way we can start doing this is by noticing the nouns and the verbs when reading through the game design document. By categorizing the nouns and verbs, this assists in writing the technical design document. Game code is generally composed of game objects, nouns, and components, verbs. This becomes the foundational structure of games. We always keep in mind that communication is fundamental to all parts of this, and as programmers, we are learning to speak to the machines using programming languages. By identifying the nouns and the verbs, we may speak more clearly to the machines in the same way we speak to people. The game objects and their components are smaller parts of the overall game system. In game design, we discussed how all games are systems. Commonly, the game system is the code which runs or drives the game. It is in charge of calling the functions related to the game loop pattern. These function calls can be considered event messages that are sent to each game object and then delegated to each component. In addition to the game loop pattern, the game software system also is composed of libraries, other systems, and programming interfaces. It provides the developer with features commonly found in games, such as user input interfaces, physics systems, and other useful software libraries. The game software system can be a game engine in most cases. The big overall structure is the game system is composed of a collection of components called game objects. Game objects are composed of behaviors called components. The game system follows the game loop pattern. It handles events for each game object for each component within. It updates each game object and for each component within. It draws each game object for each component within. Now that we have gotten that out of the way, we can move on to more structure and behavior examples. Our problem is to create a space shooter game where the player defends themselves from interlopers while traversing an asteroid field. Once again, we are going to assume that the full game concept has been written in a wiki. You can find this and more details along with this in the course notes. From that wiki, let's gather some requirements. The player must be able to control a spaceship by rotating it and moving it both forwards and backwards. The player must be able to fire a laser in the direction they are facing. Periodically, the game will spawn enemies. Enemies can either be asteroids or space interlopers. Asteroids have a fixed direction and speed that they will travel. Space interlopers are more intelligent, and they will track the player and fire lasers at them. Collision detection between lasers, asteroids, space interlopers, and the player must all be detected. When a player's laser collides with either an asteroid or a space interloper, then the enemy's health is reduced. When the player collides with either an asteroid, space interloper, or an enemy's laser, then their health is reduced. Destroying a space interloper is worth more points than destroying an asteroid. When the player's health is reduced to 0, then the game is over. The game has stages, which increase in difficulty as they progress. The current build will have 5 stages. Each stage has the same time limit, but types and the amount of enemies that spawn increase as they progress. The player must survive as long as possible while earning as many points as possible. When either the player survives through all 5 stages or when they perish, their high scores are recorded. Once again, let's start identifying the game objects by identifying the nouns in the requirements. We notice a few game objects immediately, like player, laser, interloper, and asteroid. While we do not see it explicitly written, there is another game object that works like a referee, official, or point keeper, and we call it a scene manager. Having one game object as an official inside the game can help us organize the overall rules and goals for a game. Many times we can identify this game object when we notice that the game needs to keep information managed, like points, timers, and etc. We also notice that the scene manager is also related to stages or other scenes throughout the game. Now, we can start identifying the actions related to each one of the game objects. Starting with the player, we first notice some actions related to user input. Moving the player and firing the laser are actions that must happen based on the inputs by the player. We also notice that we have a transformation component, which contains all the location, rotation, and scale data. A spaceship is mentioned, and we can think of this as being a 2D image called a sprite. We notice it mentions collision detection, and we use a simple geometry called a collider to detect collision among other colliders. Collision detection is important, but we need something that handles the collision response. These events are sometimes very specific to the game object, and so we need to write them specifically. In our case, we do need to handle collisions between the player versus an asteroid, an interloper, and a laser differently and uniquely. This will be different than the collision responses written in asteroid or interloper. Later, we discuss in more detail that there is a critical difference between collision detection and collision responses. We also see that we have a health system that will work alongside the player's collision responses. Putting it together, we can see the design for the player. From the user input, we can move and spin the player, which is handled by a translate and rotate functions provided by the transformation component. The sprite is drawn at the position and the orientation provided by the transformation component, and the collider also uses the same position and rotation as well. The collider's messages are processed by the player's collision component, and we consider the player's collision component to be listening to the collider. When a collision occurs, the collider will broadcast an event message to all the components within. The components listening to the collider will execute code based on the collision. We see the player's collision component will reduce the health of the player within the health system component. We also notice that there are two exterior dependencies that we must address. Firing the laser requires a way to create a laser game object. Notifying the scene manager that the player has been destroyed requires a scene manager game object. We need both of these to complete the player's system. So, let's move on to some other game objects. We first notice that the laser needs position and rotation data, so we now know that the transformation component handles all of this. We also need to draw the laser using a sprite. Firing the laser requires the laser to move. The laser motion component handles the movement of the laser and also the collision responses. We could have separated this into two different components, but we decided that integrating the two would simplify the design. There are many different ways to design the systems to work, and some are better than others in different ways. As long as it works well enough, then it's not a problem. This is another example where the collision responses are handled in a different behavior than collision detection. This again is handled by the collider component. We can now see the laser game object and its assembled components. We notice it is a prefab, as we need to dynamically create mini lasers for our game. We notice that the collider and the sprite both use the position property provided by the transformation component. We also notice how the laser movement component is listening to the collider. This code is combining both the movement behavior and the collision responses into one component for a more simplified design. Connecting together the two game objects, we can now see how they work together. From the user input component, the player fires a laser, which instantiates a new instance of a laser. One major detail is the connector outside of the game object that does say instantiates. Instantiating is a concept of creating a new instance of this game object, and we can think of this functionality as being provided by the game object itself. When we instantiate a new instance of a game object in our world, then it is created along with its components dynamically. Moving on to the next dependency, we can see the scene manager's code could all be simply written into one component. We are in the business of engineering solutions and not over-engineering solutions. While much of this functionality could be separated into various interconnecting components, it may at the same time overcomplicate the design and slow down the game loop. It is a trade-off between writing a few large components versus writing many smaller components. Writing a few large components can be much faster within the game loop, but limits flexibility when adding or modifying features. Writing many smaller interconnected components allow more flexibility and code sharing, but can become too abstract, overly complicated, and slow. Finding balance, much like life, is important here. Always ask, what are the troubles and are they worth the time? The functionality related to the scene manager typically deals with the constitutive rules like point scoring and timers, but also integrate the goals by implementing the win and loss conditions. In essence, they manage the rules of the game, or at least part of it. Adding the scene manager to our design, we could see how now the health system will notify the scene manager when the player was destroyed. The scene manager game object is fairly simple, but we do notice that it has a direct dependency as well. We need to be able to create an instance of an enemy game object, the asteroid and the interloper. So now, we look at the actions related to the asteroid. Once again, we see the transformation component, the position, rotation, and scale data, the collider handles the collision detection, and the sprite of the asteroid is used to draw the game object. We also note that it does have some unique components, such as aster movement, which incorporates both the motion actions along with handling collisions. Interesting to note that much of this is very similar to the laser game object, except that it has a health system which is affected by the collision responses. Now, we do the same for the space interloper. This is slightly more advanced than asteroid, but still shares many of the same components. It is interesting to note that track player component is used in a similar way as user input. This is where more sophisticated AI could be integrated for the enemies. Now, putting them all together, we can see the design for this game. We can see all the game objects along with their components and how they interconnect. This nearly feels like the entire design, except there seems to be some features missing that this does not address. We notice there are stages that progress the game further in difficulty. We do not seem to have this concept in our component design, but we have mentioned that the scene manager is used to handle this. Also, when we consider most modern games, we have to wonder, where are the menus and other graphical user interfaces? This is yet to be mentioned, and both of these require understanding another level of organization. Game objects can be further organized into scenes. We could think of these as different sections or environments of the game. different levels, different rooms, different dungeons, etc., which would contain only these game objects and these components. These help separate and organize different sections, stages, or levels of a game. When a scene is loaded, only the base game objects and their components associated with it are loaded. More can be loaded and unloaded as needed. This can help reduce load time, and scenes can be used to further structure the overall game. The scene manager helps enforce the constitutive and operational rules for the game. Many times, it does focus on the overall outcome win-loss conditions of a game. Scenes can be used to further structure the overall game. Different scenes may have different interaction, rules, and objectives. A scene manager can be used to implement the goals and rules related to a specific scene. It's a special kind of game object that contains all the relevant scene information, such as points earned. It contains the components which implement the rules and objectives, such as time limits and win-loss conditions. It also assists in transitioning from one scene to another. Finally, scenes can be organized based on a state machine. State machines can be used to outline the flow of the scenes for a game. Boxes are scenes such as menus, levels, and represent the game's state. Arrows are the actions required to move from one scene to another. Start and exit are special states indicating where to begin and where to end. In the technical design document, state machines representing the scenes are useful for showing the flow and the progress of the game. This is useful to have in the game design document. This is in addition to the component diagrams. The scene manager can be responsible for creating these transitions and implementing the scene state machine. Again, this is in addition to the component diagrams, which show the interworkings of the game objects and the components within the scenes. For our game, we can include this in our technical design document. Within the technical design document, it is useful for it to contain a scene list. Scenes should clearly indicate the name of the scene and its internal scene name, objective rules and goals for each of the scenes, and other comments related to these can be added for better clarification about the rules and objectives. Listing all of the outgoing transitions and the related criteria, for example, to this scene when this condition is true. A reference to the game object component diagram for the scene. Including rough sketches of user interfaces for menus can be useful in finalizing the design. We can start seeing an example of these details for our scenes. Here's an example of our main menu scene, which also includes the component diagram. More details regarding each game object and the associated components are provided within the game design document. Now we can see the example of level 1. We notice that this contains the component diagram mentioned earlier. Skipping ahead a few scenes, we notice that level 5 appears to be the same component diagram. In fact, most of these seem to be about the same except for the transitions, the amount of time the player has to survive, and the density of enemies. We notice that this is the same structure for Scene 2 through Scene 6. All of these are variable properties that can be set in the Scene Manager component for specific levels. Now by creating this one scene, we can replicate it and adjust some of the Scene Manager properties to increase its difficulty. Let's design another kind of game. This time, we're going to focus on another kind of game called a platformer. The main goal of these games is to go from point A to point B as quickly as possible while earning as many points as possible. Platformers were one of the most popular games in the late 80s through the 90s. While not as popular today, it remains a strong game genre for those interested in perilous parkour play. Here are some of the requirements for our game. The player must be able to run and jump around a side-scrolling 2D environment. Forces such as gravity must affect the player when either they jump or fall off of a platform. The player can only jump as long as they are touching a ground surface. The player's goal is to reach the end of the level and earn as many points as possible. The player collects coins and defeats enemies to earn points. The player only has a limited amount of time to reach the end of the level. The time left over earns the player points when they reach the goal. There are 5 levels which are rich with platforms, pitfalls, and enemies that progress linearly. When the player collides with an enemy, they lose health. Once the player's health reaches 0, then the game is over. The player can attack an enemy by throwing a hammer, which is also affected by gravity. Enemies also attacked through projectiles affected by gravity. Now, we can identify each one of the game objects by noticing their nouns. We can see that there is a player, coins, enemy, the ground representing platform, and hazards representing pitfalls. We see that there is a goal game object which the player is attempting to reach. We notice that the limited amount of time is highlighted as the scene manager. We notice and understand that this game object, which represents a referee or game official, is typically used to handle many of the rules and the data that is important to the scene. We also know that this game object will be in charge of transitioning to the other scenes later on. We also notice another game object called camera, which is associated with the side-scrolling 2D environment. In order to simulate a character moving in an environment, we can have a camera game object follow the player around. Using a camera to follow the player is a very common way to draw a scene. Now we focus on the player game object and what it does by noticing the verbs. Once again, we need a sprite to draw. User input allows us to capture the controls related to running and jumping. The transformation component holds all the data related to the position, rotation, and scale. The collider detects collision, and the health system keeps track of the player's health. We also notice a special highlighted component called the rigid body. One major detail to note: this type of game requires more sophisticated physics in terms of both the detection and response. A rigid body is a common type of component that applies classical mechanics to a game object. Keeping in mind that classical mechanics is a branch of physics concerned with the study of bodies in motion which are affected by forces. Remembering Newton's law, and especially force is equal to mass times acceleration, is critical in understanding. This component provides a means to assign mass to a game object and also apply forces, such as gravity or other external forces on them. It also assumes that the object does not deform and applies forces strictly based on a rigid body. While this may appear to be a little complicated, we recognize that it is just another kind of component that falls in the game loop pattern. In terms of design, we are not concerned with the details about how the forces are applied, just as long as they are. Putting together the components inside the player, we can start to notice some of the differences when using a rigid body. We first notice that the user input to run and jump are connected to the rigid body. We assume this will be implemented where running will change the rigid body's velocity, and jumping will apply a force upwards to the rigid body. The rigid body, again, are used to impart classical mechanics, and typically has properties like velocity and other methods such as add force. We can also see that the rigid body listens to the collider. We keep in mind that the colliders detect collision while rigid bodies handle the collision response in the form of applying forces. We also handle collision response in our own way by using some constitutive rules related to the health system within the player's collision component. Both listen to the collider, but one handles applying physical responses while the other applies handling game responses. Also notice how that there is a bidirectional arrow between both the rigid body and the transformation. In most physics systems, the transformation and the rigid body work together along with the collider in order to detect and respond to collisions. The transformation holds all the position, rotation, and scale information, which is provided to the rigid body and collider. However, position and rotations are modified by the rigid body's forces that are detected and influenced by other colliders. Each component handles a different part, but they all work together to simulate rigid body dynamics. This game object has some external dependencies, and we are going to focus on projectile as it has some similar concepts. We can start seeing the components regarding projectiles. We recognize some very common components such as sprite, collider, and transformation. All of these are once again needed to draw, detect collision, and contain location data respectively. We also notice that we have a rigid body as a part of this as well. As the projectile is being pulled by gravity, it needs to be able to apply forces. In fact, throwing the projectile is applying a force to it, and so the projectile requires this component as well. Adding this new game object to our design, we can see how the player instantiates a new instance of this projectile. We can see how this game object is a prefab or prefabricated, so that the player can create them dynamically as they are thrown. We also notice there is a message being delegated to add force at the same time. We assume at the time the projectile is instantiated that the force is immediately applied, thus simulating the act of throwing an object. Before we move to the scene manager, there's another game object related to the player that is important to discuss. Going back to the requirements, we're going to now focus on the camera game object. In the other games, the player could freely move around within the bounds of the environment. The environment was assumed to be small, never moved, and was the exact size as the window frame. However, in this game, the player moves around a much larger space, which cannot be reasonably viewed all at once. We must limit the viewing space for the user and focus on the player's location within a larger environment. In order to do this, we use the concept of a camera object. This will only draw the game objects within a specific window frame. So now we can create levels much larger than our windows. The camera game object, of course, requires a camera component, which handles drawing the current scene. This component contains all the data related to the size of the window frame and even more details such as projection type, render layers, and the field of view degrees. We also notice that the camera GO has a transformation component, which will contain its location and rotation data. Yet, there is something special we need to notice about this particular transformation. In our game, the camera must always follow the player. We already know that the player has a transformation component, which contains the position data. In fact, this transformation component depends on the player to follow it. This is a common relationship found in many games. This leads us to a few more considerations to be aware of regarding the structure of game code. Most game engines assume that every game object has a transformation component. As mentioned, the transformation component holds all location, orientation, and scale data related to the game object. Position X, Y, and Z. Rotation, pitch, yaw, and roll. Scale X scale, Y scale, Z scale. We could think of these as being the same as the move component discussed in previous examples. But more technically, it transforms the local coordinates of a game object into the world coordinates of our game. This is a much larger concept that's discussed at length later. For now, we can understand that this contains position, rotation, and scale data, and it also handles the calculation related to the transformation functions. Translate moves the game object. Rotate rotates the game object. And rescale, or just scale, changes the scale or size of the game object. With this in mind, game objects can be further organized into hierarchies. This tree structure generally links together the transformation component of a parent game object to affect the transformation component of a child game object. This is like any other tree structure in computing where it contains no cycles or loops. The topmost game object in the hierarchy uses the global or world coordinates. Any child game object has local coordinates that are relative to the parent. If the parent game object translates, rotates, or scales, then so will the children game objects. The child will follow the parent. We can also clean up the design slightly by enclosing one game object within another. The enclosing game object is the parent, and the enclosed game objects are the children. We remember that game objects are components, and we may have components composed of other components. With this in mind, we are aware that the enclosing transformation will modify the enclosed, and we can skip drawing any extra lines. Adding the camera game object to our design, we can see that there is a parent and child relationship between the camera and the player. Whenever the player moves, thus their position changes, it will change the position of the camera. This simulates the action of the camera following a player around the environment. We also notice that the camera does not have a rigid body component. We keep in mind that only game objects that need to be affected by forces directly require a rigid body. The camera does not need to be affected by forces like gravity and only needs to follow the player. We can continue to notice this concept when creating the ground, hazard, goal, and coin game objects. They only need to be able to detect collision, which is why they have colliders. But they do not need to be affected by forces. Collision detection is different than collision response. Collision detection is handled by colliders, and responses are handled by other scripts, which include rigid bodies. Rigid bodies are only used when we need to impart elements of classical mechanics, like forces, to the game object. A key tip is rigid bodies are only needed when forces need to be applied, and gravity is always a good place to start. Now, putting them all together, we can see a rough design for this game. We can see all the game objects along with their components and how they interconnect. The complexity of this kind of game is much larger in scale than the previous discussed. In fact, for sake of space, some of the game objects needed to be combined, such as ground and hazard. In the full game design and technical design documents, these would be separated. But again, the purpose of this is to make a game and not just a design. We now start to see how to put this together, but this is only one scene of our game. We can now organize the game into scenes representing the menus and the levels of the game. We see that there are 5 levels and progress linearly, and we also notice a detail not mentioned in the requirements. Some levels have a secret skip that allows the game to be beat much more quickly. These are great details to put in these diagrams, especially in the case that the game may not be linear and feature levels that branch or even loop. To sum everything up, creating a video game is an exercise in software engineering. Recognizing common software patterns is critical to quickly developing solutions. The game loop pattern is a behavior pattern facilitated by the game system. Events, update, and draw are the steps. Game systems are structured based on the game objects which contain components. This is based on entity component systems, and for games, the component pattern. Game objects are simple containers for behaviors we call components. Components are classes of behaviors that represent the actions that the game object can perform. We further organize game objects into structures called scenes that can be represented by state machines. All of this information is found in the game design and technical design documents. Now that we've seen a few examples of how to design game software in practice, we only need a few more details before we can begin fully developing a game. With all of that being said, make sure to practice speaking nicely to the machines, and I'll talk to you next time. Now it's time for a bonus round. What is a scene? A scene is a container for game objects related to a section, stage, or level of a game. What is a scene manager? A special kind of game object that implements the goals and rules related to a specific scene. What kind of structure is best used to diagram scenes? State machines can be used to outline the flow of the scenes for a game and should be included in the technical design document. What is a transformation component? The component that contains information relating to the object's location, rotation, and scale. How are transformation components related? In a transformation hierarchy, where the tree structure creates a parent-child relationship between the two transform, the child will follow the parent. Now it's time to look ahead using our forward vector. We're going to see how these concepts presented relate to some of the course assignments. For your game, make sure to identify the scenes and criteria for the transitions. Include a scene state diagram in your technical design document where all the scenes are stated and the criteria is clearly labeled for each transition. Also include a scene list in the technical design document with its name, objectives, outgoing transitions, and a link to the game object component diagrams. With all that being said, I'll talk to you next time.